Hello everyone. Today we are going to discuss about the experiment 2, that is the analysis of real-time signal using the filters. These filters that we have already discussed in experiment 1. Don't worry if you haven't seen the experiment 1 video. Now within few minutes we will be going through the theory regarding that experiment. So, hello once again. I am Sailaja Patoju, third year student of Electronics and Communication Engineering. So, the real-time signal that we are considering here is the PPG signal. Before getting to experiment, let us first know about what is PPG signal. PPG signal stands for photoplethysmogram signal. It is obtained by using pulse oximeter that illuminates the skin and measures the changes in light absorption. So here you can see the front side and the back side of this PPG sensor. So this PPG sensor, I have got a sample for you. If you can see this, you have an LED over here and a photodiode over here and LED. So the top one is the LED, which is this one, where this is the LED and this is the photodiode or the light sensor, and this is the signal, the output of this sensor. These two are the inputs. This is the VDD and this is the ground. So this PPG signal, being a physiological signal, it is harder to steal or replicate, hence it can be used for biometric purposes. This is how the PPG sensor collects the data. By shining the light on the skin using the LED light emitting diode, and the increased pulse pressure will cause a measurable difference in amount of light reflected back and thus transmitted to the photodiode. So here the light will be coming through the LED, and what we need to do is just block that light and put your hand on the PD sensor. For better results, the LED light must be placed in areas where the arteries are close to the skin. But why should we only choose arteries? Let's know. The amplitude of pulse is directly proportional to the pulse pressure. So if you can see in this graph, this is the systolic point where the blood flows through the arteries, and diastolic point where the blood from the veins is going to the ventricles. So if you see the peak, this one has the more amplitude, which means more pressure. Thus for better results, we use these points to calculate calculate heartbeat regarding our PPG signal. So each peak in the resulting signal can be identified by a special heart rate algorithm that can ultimately determine the amount of time that occurs between each successive peak, giving another measure of heart rate. Here you can see the IBM interbeat interval. There will be a system where it functions the special heart rate algorithm, where the input is the PPG signal and the output will be IBI signal, that is the interbeat interval signal. So in this experiment we will be going to consider three filters. First one, moving average filter, second one, derivative filter of first order, and the third one is derivative filter, 3-point central difference. Let's first know about moving average filter. Moving average filter is a low-pass finite impulse response, that is the FIR filter, commonly used for smoothing an array of sample data or signal. So how can we do this? Take the L samples of the input at a time, creating one output from this sample, and the output will be given to or stored into another array which gives the output, that is Y of n. So hence the equation will be Y of n is equal to 1 by L sigma k equal to 0 to L minus 1, that is we are considering L samples, x of n minus k. So as the length of the filter increases, that is the L value increases, the smoothness of the output increases, whereas the sharp modulations in the data are made increasingly blunt, that is the high frequency regions or the high frequency noises are made blunt or decreased. But at the same time, its cutoff frequency also decreases because we are smoothing the array, which means we are taking out the high frequency noises components, which means the frequency decreases. So cutoff frequency also decreases for this smoothing signal of PPG. The transfer function I have already discussed the difference between the transfer function obtaining the impulse response and the transfer function. The impulse response can be a transfer function only when there are no initial conditions, that is zero initial conditions. So impulse response h of z of L point moving average filter can be obtained by applying z transform on previous equation. H of z equal to y of z by x of z, which equal to 1 by L times of sigma k equal to 0, L minus 1 k power minus z. That is the delayed version. The delayed version, here you have seen x of n minus k. So if we take the z transform of this, we'll get x of z into z power minus k, which is what we have written here. So observing the performance of this filter by doing the frequency analysis of the impulse response of h of z, and with considering different values of samples, that is L in the MATLAB, we will be getting this as the magnitude response and this as the phase response. If we vary the length, that is L, as 2, 3, 4, 5, 6 and 7, we will be going to get these. This is for 2, 3, 4, 5. As we increase the number L, the magnitude response, the frequency decreases and the peak will be 1, and this width also decreases. So next we will be going to discuss about derivative filter. Derivative filter is a periodic band pass filter, which is finite impulse response filter that provides a quantitative measurement for the rate of change in sample data or signal. So the use of this derivative filter can be seen through as the rate of change of pixel in image processing. Derivative filters, here we will be going to discuss about two: the first order derivative filter and the 3-point central difference filter. Let's first see first order derivative filter. It is a Cauchy filter and LTI filter. LTI stands for linear time invariant filter, whose output depends on the current input and the previous input, which shows the causality property. It is basically used to highlight high slope regions of the signals. So when we have to emphasize the high slope regions, we will use derivative filter. We can use the first order or the 3-point central difference. Let us go through the 3-point central difference. It is also a Cauchy and LTI, that is a linear time invariant filter, which considers twice unit delayed input sample about an input sample and itself to produce the output, and therefore it is quite more accurate than the first order difference filter. Let's see the equations for better understanding. The first order derivative filter, the equation will be y of n equal to x of n minus x of n minus 1, and the transfer function can be obtained by applying z transform, which is y of z equal to x of z minus x of z by z. By considering y of z by x of z, we will get 1 minus z inverse. If we consider the 3-point central difference, the equation representing this filter will be y of n equal to x of n minus x of n minus 2, and the equation for this transfer function, the equation for the transfer function of this filter is y of z equal to x of z minus x of z into z minus 2, z power minus 2. Hence h of z equal to y of z by x of z equal to 1 minus z power minus 2. This is the magnitude response. Here the blue one that is there is indicating first order difference, and the red one is indicating the 3-point central difference, and the corresponding phase responses are like this. So let's go to experiment questions. Choose a filter to smooth out high frequency noises present in the signal. As we have already discussed, to eliminate high frequency noises, we have to use the moving average filter, which averages about certain number of samples, that is L number of samples, and gives the output as single sample where the high peaks can be reduced or made blunt. In the previous experiment, we have considered the signal, or the x of z samples already given in the Arduino program, but now we have to collect the samples from the PPG sensor. So first we have to initiate an array x offset and y offset. So we have to define arrays x offset and y offset, input and output, and the fraction and the length of the signal, that is the input signal, and what will be the length of the samples that are to be combined together or averaged together, and the input pin, that is the A0, which is the analog pin that is used to collect PPG signal, and we'll be communicating, that is the system is communicating with the Arduino board at a baud rate of 9600. And if we come to the program, first of all we have to collect the samples. Here, to collect the samples, we are going to write a for loop with a delay of 10 milliseconds, and we use analog read as the signal that we will be getting is an analog signal, and the pin is also an analog pin. And after getting this data, we have to do the averaging thing. So first of all, we'll write a for loop for y and another for loop for x, and we'll be adding them and then dividing by L, which gives the averaging operation, and we serially print x and y. These are the things. This is the x signal, the original PPG signal from the sensor, and this is the smoothed out signal. As you can see the difference, this high frequency noises have been reduced. And the next one is choose a filter to emphasize high slope portions in the signal. As we have already seen before in the theory, derivative filter of first order is used to emphasize high slope portions in the signal. So first of all, we have to collect the signals, for which we define an array x of 1000, that is the 1000 samples we are going to collect, and y of 1000, which gives the output ya and yb. We'll have to calculate the size of the array, that is the input one, and we have to initialize a pin A0 to get the PPG signal, and we'll be communicating with the system, that is the Arduino will be communicating with the system at a baud rate of 9600. And we have to first define a function, moving average function, that is float f, which is the input, and int n float, these two. Sorry, f is the fraction, here x is the input, y is the output, and n is the number of samples. So first, for int I equal to 0, we have by I equal to 0, this is initializing every element of the array to 0, and then we have to do the averaging operation that we have already seen before, and then we will be going to run the void loop, and in this loop first of all we'll take analog read pin, and then we'll do the difference operation of first one and second one, because this is the first one is indicated first order and the second one is 3-point central difference, and we'll be going to print all the input in this, the output, and this is the first order, this is the second order, which gives this is the moving average one, this is first order, and this is the second order. If you see, it is the second, it's not second order, it's 3-point central difference, which is much more specifying the high slope regions. And design a moving average filter with L equal to floor of 0.8 times of n to extract baseline drift component. So first of all, we'll be giving an array of x, y and z, and x will be the input, y will be the moving average ones, and z will be the difference one. So the system communicates at a baud rate of 9600, and this is the analog pin. We will be getting the PPG signal through a loop and a delay, and we'll be doing the averaging function with L equal to 8 samples and averaging filter with L equal to 800 samples, because here we'll be going to get with L equal to 0.8. So after getting this, we have we'll be having moving average filter output in Y and Z, where Z is our required thing. If we subtract Z from Y, then we'll be getting the baseline drift component that is sure to be displayed. This is the graph. This is the baseline drift. Blue is the original signal and red is the smoothened signal. So output, the final part of this experiment is to find the output of the signal processing system, which performs first order derivative filter and then performs moving average filter operation. So we have to consider the arrays and the size of the array and void setup. This is the serial begin and the void loop. We have to collect the samples and then we have to do the difference operation first, and then we have to go to moving average, which gives the smoothing signal, and we have to print both. Here this is the signal and this is the moving average, first order difference filter, and this is the smoothed output of this one. Thank you. Hope we'll see in next video.